Hello. So everyone here at 426. Anyone here who is not computer engineer? Everyone computer engineer? Okay. So I'm going to talk today about the logistics for the class and some introduction. There's no lab this week and next week. So we will have the lab starting on the first week of the reason for that is that we haven't covered enough material yet, and the first lab will be about assembly language. So by the end of next week we should cover enough material to prepare for this. We will have labs from now all the way to the end of the class. All labs are done individually. There's no collaboration except lab 4. Lab 4 is the only one that you're allowed to have a partner after you talk to someone in the lab or do it individually. But everything else is done individually. Labs, assignments, tests, everything is done individually. Okay. So the Canvas site should have most of this information if you logged into it. The textbook for the class is the Patterson book. It's not required. I'm not going to get any assignments from that book, but most of the materials we covered in the class in the past year is from this book. I covered additional material outside this book, but about 95% of the material that we cover in this class is from this book. Make sure if you're going to get it, you get the 6th edition, the last one, which is 2020. Most of the material that you need is already in the course webpage at Canvas. You have all the lecture slides all the way to the end of the class. I haven't uploaded the assignments for the labs yet. I'm going to upload them at least 1 week before the deadline for the assignment for the next. I have the distribution of the class materials, description of the course, description of the way we're going to grade the class, all available in this service. Participation and attendance is required. So I'm not going to take attendance every time, but randomly I'm going to take an attendance sheet or make a quiz, 5-minute quiz, which will replace attendance. The reason for that is that you can see here the correlation between attendance and the grade for the different levels. You can see the clear trend here by the number of absence and the GPA. I have been seeing this over here. I've been teaching for 15 years, and this is a persistent trend. So the more you attend, the higher your grade will be. There are some prerequisites for this class, the 364 or the 311 from the computer science. The topics that I'm assuming that you have already familiar with is the binary logic, binary gates, some programming skills, because some of the classes will have programming, some of the assignments will need some programming skills, understanding how to translate between a pseudocode and assembly language, and vice versa. We're also going to use some high-level programming for some of the labs, especially the last lab where we're going to do the memory hierarchy implementation. You should know the different representation of numbering, the different numbering system, binary, octal, decimal, and so on. Basics of Boolean algebra, gates, flip-flops. Although whenever we need it, I will just provide a short introduction to these topics, but I'm assuming that you should have the background to understand what I'm talking about. What's the difference between sequential and combinational logic, basic microprocessor and assembly language, will be important. So I'm just jump, assuming that you have the background for this class. What we're going to cover in this class is the basics of designing a micro computer or a microprocessor. So basically, at the end of this class, you should be able to build your own microprocessor. And in fact, one of the labs will be directly about that. So you're going to build a 16-bit microprocessor from scratch using HDL and ensure that it is working and it's accepting a assembly code, executing it, and writing the output headings. We're going to go through an introduction of computer system organization, history about the computer systems, the different types of computer architectures, how we evaluate system performance, how we make the system work faster, how we make improvement in the performance by adding some parts of the system where there are bottlenecks, where there is more emphasis on some aspects of performance than others. Performance can be evaluated in different ways. We can talk about speed, we can talk about cost, we can talk about power consumption, we can talk about throughput, we can talk about reliability. All of these are different dimensions that define the performance. And for each category of computer systems, we will be emphasizing on some of these dimensions more than others. How to evaluate this, how to figure out which part of the system that you need to improve, and what do you expect out of this improvement in terms of overall performance improvement. This will be the topic for next week's class. We're going to talk about assembly language and the instruction set design, what defines the instruction set architecture, how we, the basic dimensions of the architecture, register files, the size of the memory, the number of instructions, the type of instructions, and so on. And we're going to talk about arithmetic for computer, how to perform addition, subtraction, multiplication, and division for both integers as well as floating point numbers, which is fractions. The core of the class is about this part, starting from the processor design and implementation. We're going to take the first basic architecture, which is a single cycle implementation of a processor, discuss how we make the single cycle implementation, put these different components together to form a microprocessor. And then we're going to talk about the actual realistic implementation, which is the pipeline implementation that is being used in almost all microprocessor nowadays. How we divide the processor into different stages and perform pipeline implementation. We're going to talk about, as we talk about pipeline implementation, we'll talk about the parallel architecture, multiple architecture, and how that can improve the performance and how they work in realistic systems. The last part of the class most likely will be the memory hierarchy, how the memory is organized, starting from the cache memory, which is just directly adjacent to the processor, all the way to the hard drive and tapes that are being used for external storage, and how we go from small and fast and expensive all the way to big, slow, and cheap memory, and how we give the impression that this memory is formed as a one block without affecting the system. If we have time, we're going to talk about interfacing processors, input-output interfacing, and the peripherals, how they are connecting to the processor system using bridges. And we might talk about multiprocessors and the next generations of processor architecture related to this. What you can learn is how a program is executed and what are the hardware involved in the execution, how these components working together in a systematic way to execute instructions, perform the operation correctly, and provide the output to the system. What are the definitions, different definitions of the hardware-software interface? How the software is translated into information that the hardware can understand and use to modify the system state. How to define the program performance all the way from choosing the algorithm, choosing the processor, choosing the compiler, choosing the architecture of the processor, and how choosing the hardware can improve the performance. Which part of the hardware have most impact on performance? In some cases it's the memory, it's the cache memory, some cases the parallelism or the pipelining, and which part of the stages will have different pipeline stage will have the most impact on improving the performance of the system. We're going to talk about parallel and multi-core processing, how the processor is designed into multi-core architecture, and even within the core there is parallelism, which is called multi-issue, where you can run threads in parallel in the same core. And so we're going to discuss this and how it's being designed. When we start talking about these more advanced topics, we will go incrementally, showing how the basic architecture, the basic single cycle implementation can be adapted and can be modified to become a pipeline, and from pipeline become a multi-issue, and from a multi-issue become a multi-core. We're going to go into stages all the way until you see the full picture of the processor design that is compatible with the current trend in microsystem design. You should know more about the memory hierarchy, how the cache memory is divided into different levels, level 1 cache, level 2 cache, level 3 cache, how they are interfaced with the main memory, and how the main memory is interfaced with the disk or external storage. What do we mean by page failure? What do we mean by a cache message, and so on? This terminology that you can hear about you get more involved in choosing processor design and what they mean in practice. This is how the grades are distributed. They will take 20% of the overall grade. Quizzes and attendance will be 5%. Midterm exams, we have two midterm exams. One will be at the end of September, and the other one will be end of October, early November time. And the lowest test grade will count halfway, so give you a better chance to get a good grade from the midterm exams. Midterm exams will be in the same class time. It will be 1 hour each, and it should cover only part of the class, not the whole. So first midterm will take all the material that we cover all the way until the midterm exam. Second midterm will be the material covered from the first midterm to the second. The final exam is comprehensive. Everything will be covered, but it will have more emphasis on the topics that we covered at later part. Labs will cover 25%. They are distributed equally, except for lab 4, which counts as 2 labs. Because of the amount of work, lab 4 will take 4 weeks to finish. So because of the amount of extra work in that lab, it will count as 2 labs. And there is a chance that you can get a bonus grade if you do some extra work. So for example, I'm going to ask you in lab 4 to build a microprocessor, 16-bit microprocessor, and then if you go, this is going to be a single cycle implementation, which is a very easy implementation, but if you give the effort to make it a pipeline or LMS similar to that, all of that will add bonus to the extra bonus to the lab, which can help you to compensate for any missing grades and other things. Quizzes will be rare, but it might happen. It will be in the middle of the class, and it will be about the materials that we covered during. So I'll come like after half an hour of the class and then give you a sheet to run a quiz. And that will be just a single or question or 2 questions, not beforehand. But it's most of the time you get the answer right, and it will be used also as kind of attendance training. This is an upper level course. We cannot cover everything about microprocessor in one class. It's just impossible. This will be the first class in a series of two classes. The other one will be a graduate level class. We'll talk about advanced microprocessors, the one that are being used for graphic cards, for nowadays for data analytics. They are using this very advanced, massively parallel processors with thousands, if not tens of thousands of internal processors working together to perform computations. It's been used for most of the advanced AI technologies, and that will be the topic for the graduate. For this class, we will cover the basic architecture for a microprocessor, how this microprocessor operates, how you can build your own one that fits specific requirements for whatever purpose you are designing the microprocessor for. And we've covered some advanced topics, but it's not going to cover the most state-of-the-art technology that is being used for data processing. That is going to be covered in the graduate level class I'm going to give next semester. But this is still an upper level course. There's a lot of materials to cover. Some of the materials I will leave it up to you to figure out. Most of the basic materials I will go through, and I will go through in details. I don't use slides as I explain things, except for the first class. I usually use the board, right, and go through every step to explain everything directly to you. But you still need to look around and look for more information, because there's a lot going on the area of processor design and processor technology that can never be covered in one or even two classes. So you have to look around for some external information, and I will be purposely ask you to some parts of the class to read about it by your own. So, for example, I will give how multiplication is being done for integers, but I will leave it to you to figure out how division is. Because division is done in the same way. Multiplication is successive addition, while division is successive subtraction. They are very related to each other, so once you know one, you should be able to understand the other by yourself. Still, if you don't understand something, if you went out and find it too difficult to follow, you can always come back to me, ask me in the class or in the office hours, or just send me an email, and we can arrange for a meeting to discuss whatever things that you couldn't catch in the virus. Always ask questions. Don't let me go through a topic without you figuring out what I meant by that and you fully comprehend that, because things are building over each other. Whatever I'm going to cover today is going to be used tomorrow and the next class. So if you skip something in the middle, it will help you throughout the rest of the class. And make sure that everything I'm covering, which I'm going to go with a lot of details, that you understand. If something is not clear, stop and ask me again and make sure that you get the picture. We are not allowing any collaboration. You can discuss your work, but don't show your answers to anyone. Don't look online for solution. Don't use external tools. I'm quite capable of figuring out if you do that. So make sure that you the assignments and the labs are not that difficult. They are very easy, and they are meant for you to make sure that you follow up the materials I give, and they are not challenging by any means. So put the effort and try to do your part. Make sure that you understand what's going on. And usually I'll give the solution for the assignment after 15 days. So again, if you look at the solution and you couldn't figure out why everything is solved this way, or the solution is not clear, you can come back to me and ask the question. Don't show work, don't copy work. As I said earlier, all work should be done individually. You are not supposed to collaborate, except for lab. This is the only lab that you are allowed to have a partner to work together on building. But all other labs, all other assignments, So that's about the class. Any questions? Anything else? Yeah.
Will you have a lab report for our lab?
Yes. So every lab will have a lab report, and it will be graded the same way the assignment will be graded. We have the rubric for grading the lab already on the website. You can see how different ways are distributed around. But the lab, the report is not the lab, because some of the labs were required to write a program or write a hardware code and synthesize that in a board. So the main outcome is the program or the hardware component that you get. Still, we're going to look at the report, and that is counted as part of the grade. That's not the full grade. Any other questions? Alright. So, what is a computer? A computer is just a huge finite state machine. And a finite state machine is a digital system that has finite set of states. That's where the word finite comes. Finite doesn't mean it's small. Like the typical computer system will have trillions and trillions elements. So that's it's still finite, but it's a huge. You cannot comprehend it directly by looking at it as a full system. You have to look at it as a hierarchy of components. And the top level view of that system is an input-output device. What input is it that you provide for a computer? If a computer system is an input-output device, what else do you need that you provide for it? Yeah.
Mouse and keyboard.
Events, yeah. Events that come from the mouse, the keyboard, the network, the printer, and also the software, which is trying to produce this event and provide an output. And what could be what output are you seeing? Yeah.
Display the monitor.
Yep. Displaying something on the monitor, printing something in the printer, a message being sent over the network. All of these are outputs that you are displaying by SIM. So it's a big input and output system. It's a variety of inputs from a variety of devices, mostly controlled by the user, and provide an output that is mostly used so as a digital system, its main function is to execute a set of predefined instructions. And the software here is the core of the functionality of the computer. So basically your computer is executing software in order to process the input and provide what kind of instructions there? Usually we have three major types of instructions. Arithmetic instructions, which deal with both integer arithmetic, just integers, or floating point arithmetic, which include the fraction as part of the number. They use different mechanisms to handle it. And we're going to talk about how these arithmetic units are working. So for integers, it's called the ALU, arithmetic and logic unit. But for the floating point, it's the floating point FPU, which is the floating point unit, which is totally separate from the ALU and is directly dedicated for dealing with numbers with fractions. Arithmetics include the add, subtract, multiply, divide, square root, and other more sophisticated kinds of arithmetic, including also the logical operations like AND, or not, and so on. The other class is the memory access, where you are trying to write and read from the For the computer, it does not see a memory directly. It sees only two parts of the storage. One is a set of register files, that is a number of fixed registers that are being used for storage of different values temporarily, or the adjacent memory, which is the cache. So it sends to a memory address and it expects that to be written to that particular memory address. And the last one is a control, which is containing the conditional and unconditional jumps. Conditional jumps like branch is equal, branch is not equal, branch is greater, branch is not greater, and so on. These are they will branch out of the sequential execution based on a condition that comes out of the previous instruction. So it compares to numbers. If they are equal to branch, if they are not equal, you continue to execute, and so on. There are different conditions that you can employ. Unconditional is just jump. So you jump and to a specific location, and from that location you continue to sequentially. Even jump has a different category, because you can jump absolutely to a place and just leave it like that. And there is jump and return if you are calling the subroutine, which will allow you to return back after you finish the subroutine to continue the execution from the point that you jumped. So we're going to discuss these categories and the other different. But for all processors that we're going to deal with, we have these three classes of instructions: arithmetic and logic instructions, memory access instructions, and the control instructions. Other processors we add to them, there could be some graphic display instructions, there could be some data processing instruction that is being used, more advanced instruction for signal processing, for example. There could be additional classes of instruction, but all processors that you're going to use, from the very small ones that is being used in your appliances or cell phones or tablets, to the big ones that are being used on supercomputers, they all have these three general classes of static control and memory. What is an instruction? It's just a set of views. That's all what the computer is. But they are defined in a format that the computer understands. So you get, for example, if you are dealing with a 32-bit instruction system, the instruction is 32-bit and it's divided into fields. One field will be the opcode for the instruction. Another field will be what kind of registers are used. Another field could be a constant. Another field could be the memory location that you are doing. So these ones and fields are divided into fields, and that division is specific to the computer architecture that is able to execute. So how these ones and zeros are, these zeros and ones are interpreted are dependent on the processor or the architecture that is. So the one Intel will interpret them different from an ARM processor, from a NIPS processor, from an M2 processor. Each one has its own definition of how to interpret these zeros and ones. We're going to talk about this later. So when we talk about computer architecture, we talk about how a different set of components are being put together to perform the function of the computer, which is executing software and producing output. But there are different aspects of computer architecture that are kind of universal, that define what is this architecture and how you can compare it to other architecture. For example, we can talk about the number of registers. Some architecture will have 32 registers. Some will have 64 registers. The size of the register is another dimension. Some computer architecture will use 16 bits. Some would use 64 bits or 32 bits. What kind of instruction? Is it simple instruction? Or it's a complex instruction? That's another dimension of defining the computer architecture. Does it deal directly with memory? We can talk about this and more about how computer architecture is defined by different aspects that all together identify this architecture. Um, there are many ways to build a system, computer system. It's not a science, it's more of an engineering. The difference between science and engineering is that science is precise. You have a specific set of rules or laws that you have to follow in order to do it. In engineering, you still have these laws and like kind of recommendations of how to build things, but the decisions here are more complex and involve many parameters that there is no single way you can achieve a design. And even there is no single way that you can achieve an optimal or an efficient design. There is several ways you can do this. For example, at a given time, a complex instruction set architecture was perceived to be the best way to build a computer. Nowadays, it's a more simplistic. We found that simpler instruction sets and smaller number of them are better in terms of speed as well as the size. And the size of the processor is always measured in terms of the number of transistors we use for it. And the size affects the cost and what? The power, yes. How much power, which is very important if you're dealing with small devices like cell phones or appliances. Power is huge. It's not a major issue if you're talking about a desktop. It's a major issue if you're talking about laptops that is on a smaller device, but not the issue for supercomputers or server computers or for this. So there are many considerations that you need to take into account. Speed is one of them, but it's not the only one. And even speed is measured in different ways. There's the speed of single program execution, because you are assuming that this is what is important for a desktop computer. Because there's a single user at the top, which is you working on the computer, and you want to ensure that when you execute something, you come up with the result. But there is another way to measure performance, which is the throughput. How many parallel users can the system? This is very important if you're dealing with business server, like Google search. You want a system that can handle millions of, if not billions of searches simultaneously. This is not an issue in this computer, but it is an issue in server computers or web servers that are being used for handling millions at a time. And so even for the speed, it means different things. Speed can be measured in the time for executing a single set of instructions, or sequence of instructions, or it is how many users it can accommodate and work with in that, which we call the throughput. Other than the speed, we are concerned about the cost. So it can be an issue, especially for small devices. We're also concerned about the power consumption. Again, for smaller devices, this is an issue that we need to take into account. We also concerned about reliability, how the system is reliable, especially if you are dealing with server business. Because when your system at business is down, it goes to business a lot. And that's a big deal, because that can make a difference between business that is reliable and perceived to be reliable for the user, and a one that is not reliable and will be affecting soon, and probably the business will end over. So reliability is very important, and how to deal with this is a different kind of aspect of design choices that you have to make as the person responsible for making a decision about which system to deploy and utilize for whatever your company is specialized. So as someone with a computer architecture background, you might be assigned the task for selecting a system for the business, for the company. And you're just not selecting a system based on your as you like it or not, but you have to justify also why you choose it based on what characteristics you think the system will be better for the scope or function that the company is performing compared to other systems. In addition to choosing the system, you might be also asked to update and upgrade it. And then you make a decision again, which part of the system should I upgrade, the hard drive, or the memory, or the processor, and how these choices will impact the overall performance. Why I choose this particular one? Because I have a fixed budget, and I need to make sure that this budget is directed toward the components that will improve the system. So you will be asked to make an informed decision about hardware systems and platforms that you will use for your company, and the knowledge you're going to take from this class will be quite essential, identifying how to improve the system performance, which part of the system needs to be improved, and what do you expect out of the system as a result. The types of computers that you're going to deal with as you go out and start your practical life varies from traditional personal computers, the one that you're all familiar with, desktops or laptops, and they are typically designed for a single user, and they are directed toward a set of desktop applications, which can range from basic publishing and editing and so on to media and entertainment and so on. They are organized in different categories depending on the set of users that are interested in this category. There are different media computers and personal computers that are used for example, work at home. But they are all sharing the same characteristics. They are all designed for a single user. It could be multiple users using it, but they are single user at a time using it. They mostly focus on the speed. Reliability is important, but not as much. Cost is important because you don't want to get something very expensive for the single cost that you just put computer with. Unless, of course, it's a media or a gaming computer where you need some more expensive graphics like cards and other accessories. The other type that you're going to deal with, mostly as part of your business work, is the server. These are computers that are designed into a server unit, and these units can vary in size. But they put in a server rack, and these racks can be stored in a server room, which requires some specific kind of cooling requirements and maintenance. But these server computers are focused on multi-processing or multi-user performance, which is the throughput, one thing, and the reliability, which is another important thing. So, for example, in the desktop computer, when your hard drive fails, your hard drive is going to lose the data. That's not a big deal. You can try to recover it somewhere else, or if you have that stored in somewhere, some external drive, you can put it back once you fix the hard drive. But for a server computer, the time to stop the server and fix it while it's idle and no user can use the system is critical for the survival of the business. So server computers are built with redundancy as a core concept. So hard drives are not organized in the same way as a personal computer. They have different redundancy levels and they require some kind of cold storage architecture in which when a node is falling or you have a node failure, it should be able to recover automatically and keep the system working without the user feeling the effect. Supercomputers are used in labs and in academia for performing very intense computations. Mostly it's mathematics being performed, and it's being used for simulation of weather, simulation of advanced weapons. It's being used recently for a lot of generative AI applications that is being used to nowadays for helping in development, automation of development. The supercomputer is not directly designed as a server computer to deal with multiple users or billions of users as a server computer system is designed for. It still have multi-users but not a large number of users. It is intended to perform a lot of parallel computation for the same or set of users. So it's high performance, a lot of ALUs, a lot of FPUs, and it's super fast network architecture that allow these multi-core or several cores to work and communicate together in a very fast way. And the last one is the embedded computer, the small chip that is being used for appliances, smart appliances nowadays, and for cars, for airplanes, for toasters, for cell phone, tablets. These are designed for power, limited power consumption, small size, and also cost is the major factors here for this embedded. How many embedded processors do you think exist on typical cars? Average about 50. So there's 50 embedded chips in the modern car. Used for anything from braking to opening doors to adjusting motor conditions and so on. And so it's a very sophisticated system. Embedded computers are used for cars and airplanes. Airplanes are huge now. And they are just keep growing in size. Nowadays, everyone is pushing for a more smart, more autonomous operations of these systems, and that will put a load on the number of embedded computers, and also on the network to allow for coordination of these embedded computers or embedded systems as much as possible without human intervention. This shows you the trend of using computer systems. Smartphone is the fastest growing area for computer devices. PC, excluding tablets, is kind of flat. Tablets start to pick up in the 2010 and then again second. But yeah, most of the embedded devices are being used in smartphones and more or less nowadays are called the Internet of Things, where a lot of small devices are being used in various aspects of house, buildings, and even cities to coordinate between different processes and give a more efficient use of these systems. Yeah, so post-DC era will be focused. You'll see a lot of personal mobile devices growing in market, and also the cloud computing. Cloud computing in which we utilize cloud architecture, which is computers connected to the network to perform most of our computation. It's been used by users like you. If you want to store your stuff in the cloud for some reason, or it can be used by the business. Some business will use some of the web services available by some of the cloud providers like Amazon, Microsoft, and Google. They have their own kind of cloud architecture and cloud services that you can combine together to form the service that you want for your business or for your personal users or for your research if you are doing research. This is sometimes called the software as a service because you're not putting the software in your computer. The software and the execution are done in the global servers, and you just get the results. So some of the initial processing might happen at your front-end computer, but most of the processing are happening in the cloud system. And renting the platform or the hardware, the memory, the storage, the processor to perform certain tasks, while you are providing your own software. Now, we're going to talk about algorithm performance in more detail, but for now, just understand that performance are dependent on many choices that you are doing throughout the development of the system, starting from choosing the algorithm to run the system. So, if you're doing a search algorithm, you want to make sure that you are using the most efficient search algorithm for the domain you are doing. And then, assuming that you get the best algorithm to implement your search, the next part is to choose the best compiler. Whether or not you should use an interpreter or a compiler, and if you choose a compiler, which one? And you should be aware of the different compiler types, which is dependent on the programming language, of course. But also you should be aware of the compiler options that can be tweaked for a specific platform in which this program is used. And after that, after the choice, then you need to choose a processor, whether you're going to use a standard processor or a more complex processor, and what amount of memory will be ideal for executing this kind of application software. The choice of the processor and the memory system should be as good, but not should be as good as needed, but not more, because these are expensive. These are it's not good that you choose a weak memory that you are utilizing when you think of it. That shows a lack of understanding. So you try to get the ones that fit your budget, one thing, but also the ones that are more efficiently fitting. Because you usually have a limited budget, and like the way you can distribute that over different components can significantly affect the outcome of it. And then the I/O system, in case the algorithm or the system you're dealing with is interfacing with an I/O system, like a display or any kind of interface. This I/O system and the latency of this system can contribute to the overall perception of performance of the overall. Let's talk about several ideas that together will contribute to designing the most efficient processor for a given application. One thing is the Moore's law. We try to utilize the advantage of increasing density of transistors per chip, but being aware that it is starting to saturate, because we have been shrinking the transistor to now a level that cannot be physically reduced anymore. So Moore's law is coming soon to an end, and the only substitute for that is what comes later, which is the parallel more cores or pipeline, more stages per core, using prediction to predict what will be executed next and be prepared. Make the common case fast. If you are using, your application is using a lot of arithmetic, then you're more inclined to emphasize on the arithmetic and logic unit to make it better than dealing with the memory. So make sure that you understand what is the common case for your application business and how you make that the fastest part of your hierarchy of memory, how you utilize that to make sure that you design it in a way that will improve the performance of the memory, because memory in most computer systems is the memory. It's not the processor. The processor is very fast compared to just the memory is, especially if you have a lot of I/O memory kind of data exchange, that will significantly bring the performance of the system down. So designing the memory for a system with heavy memory requirements will be crucial to the overall. And finally, we deal with dependency. dependability based on making the components as complete and as correct as possible, but also improving the dependability based on by using more redundancy or more components. For example, you can have 3 or 4 hard drives that are storing the same amount, the same data. So if one of them fails, you can always switch to another hard drive to get the same outcome or the same data without interrupting the performance. There's other ways that you can improve the dependability, but mostly especially for server systems, it is coming through redundancy, putting more units, and usually in that situation you have something called active and passive replicas of the system. So you have some of the servers just duplicating exactly the other servers, and some of them will be active, means that they are ready to switch to right when you need to, and some will be passive, means that they will be staying idle for a while, and then they can be restarted as needed to replace faulty units as we're going to talk about this hierarchy of programming interfaces, starting from the hardware, which is for us the memory and the processor system, and then we have the system software, which is the operating system and the system services that is being used to help with compiling and executing programs. And then at the outside is the application software. This is the program that you write and the application that you execute to run this kind of tasks. We're going to talk about high-level language and how it will be translated into the hardware representation for a machine code. You should be aware of how a high-level language like this, C, is translated to an assembly language. But we're going to focus on this translation between the assembly language and the machine code. So this is assembly language, which is designed to perform certain assembly code, which is specific for the processor, and then convert that into a sequence of zeros and ones corresponding to each the multiplied immediate here is translated to 32-bit numbers. So we're going to talk mostly about the assembler function, which is taking an assembly language and convert it into the machine. And how this zeros and ones are organized in a way that convey the information in this instruction. The compiler is the one that compiles from a high-level language to a machine. So this one hides from you the architecture. So you can take the same program and run it on a MacBook or a desktop PC, and the compiler is taking care of translating this high-level code, which is the same for both machines, into an assembly code, which is specific, one that can only run on Intel processors, for example, versus the one that can only run on M2 processor. And then with the assembler, which is part actually of part of the system software, so the compiler and assembler is usually part of the system software, is the one that is translating this assembly code into the binary machine code that is being used under the processor. In this class, we're going to focus on the main two processor components of the computer, the processor or the CPU and the memory. We might talk a little bit about the input-output devices and the interfaces for that, but this is going to be this is not going to be the focus. We're focusing mostly on these two parts. And within the processor, we have the control, which is designing or deciding which part of which components will be used for each instruction. So if it's an ALU instruction, then you're going to direct register values into the ALU, execute the code, the operation, and then get the output and store it in a memory. That is decided by the code. The data type is how these components are connected, how the register file is connected to the ALU, and how the ALU is connected to the cache memory, and so on, in a way that will allow these different instructions to be used. If you look more in detail, this is the CPU and this is the memory part, and that's what we're going to talk about in the last part of the class, which is the cache hierarchy, the memory bus, and the main memory. Memory bus will also contain the memory controller, which is controlling how the cache and main memory exchange information. This is the I/O system, and it is managed through an I/O bridge. And this I/O bridge is using the I/O command to the corresponding device through an I/O bus. And this I/O bus is where different parts of the system connect. So that would include the network interface, the network card, the graphic controller for the graphic card, and the disk controller that is used to manage the hardware, the hard drive and the external drive that is connected. So this is data head is the one that performs the operations on the data, but the controller is the one that's selecting how the data is going through this sequence of units in order to be executed. This is an example of a processor, not a very modern processor, but it's relatively new in Barcelona. And you can see here it is designed into a 4-core processor, identical 4 cores. So this is easy to clear here. And that's the first core here. And you can see here, this is the floating point unit. This is the one that is being responsible for executing floating point arithmetic. This is where it deals with memory, load and store. This is the memory access part. And we have within the core level 1 data cache. Level 1 is the fastest and smallest cache memory. And here is the execution part, which deals with logic as well as integer arithmetic. Here is the fetch and decode branch part, which is the first part of the pipeline system. And level 1 cache is divided into data cache and an instruction. So you put the data in a separate place than the instructions. Level 1 is specific to the core as well as level 2. But level 2, the difference between level 2 is that it's outside. So basically this is level 2 cache here. And it's not divided into the data and instructions. It's mixed. So there is only one cache at this level. We have a level 3, most modern processors have a level 3 cache, which is shared between the 4 caches. So level 1 and level 2 are per core. Level 3 is shared between the largest part and the slowest, because it's outside the core. So it takes a lot of, there's a wiring delay here. So that makes it the slowest, but it's the largest. And then they are interfaced with the memory through some kind of bridges here that allow you to connect to different memory interfaces, DDR memory. Node bridge is the communication unit that allows for connection between the cores. So this is how the different cores are talking to each other, or exchanging. So at the end of this course, we should have covered everything that is part of this design. We should look exactly how this FE unit is working, how the data cache is working, how the load is working. So all of this will be defined in the This is the Apple A12. Not as advanced as the Apple M2, but it also shows you the different cores. The main difference here in the Apple processor is that it includes the GPU in the chip, which is not the case in AMD. And the new AMD processor will have GPU in the chip, but and as it's a thing that will allow the graphical processing unit to be called directly called picture assessment. So picture here and this is what it's called. It's just differently. Starting from the early DRAM from the 70s, 1970s to the 2000s. Starting from the 16K, that's the most you can get for your system, to now 16 gigabytes. Like in terms of technology improvement, there is no engineering system that outpaces the advances being done in the microprocessor and microelectronics. So, like in 51 compared to 51 performance, you have 250 billion times better performance. You cannot say that on cars or airplanes. They are better nowadays. Cars are airplanes compared to the 1950s. Cars and airplanes are maybe 10 times better, but nothing comes close to 250 billion times. That makes it the fastest growing technology, and it will continue to improve. This is a very dynamic area that requires you to keep updating your knowledge and updating your information because it's just very fast changing business. So what to do as a computer architect? As I said, you are designing a computer as needed. So if your domain requires you to design a computer specific for a given application, you should be able to do that after this. You can build your own substitute architecture. You can build your own computer from basic components like register file, ALUs, memory, and branching units and so on. You can also make informative decisions about which part of the system to upgrade or replace as a user. You can make again informed decision comparing different alternatives for the system that you buy from the company. And you can identify also the bottlenecks on the performance. So you should be able to perform certain tests, and from this test you should be able to identify what is slowing down the system and use. So all these aspects of computer architecture design will be discussed in this class, and we'll start next class with dealing with the performance issue. So we're going to talk about how performance is measured. We're going to focus on two different processes: the speed and the power consumption, and the benchmarks that is being used nowadays for dealing with that, and how changing different processes would affect the overall performance. This will be the focus of the next few classes, and then we're going to move directly after this, talk about computer arithmetic and instruction architecture, and then we're going to move to the actual system design. Okay. So again, this week and next week we don't have labs, so I might take more time than the 50 minutes, a little bit more, in order to cover as much as possible because we have a lot of material to cover. So next class I might stay a little longer, the same for next week. But starting from the week after, we should stick with the 50 minutes time for class, and we should go directly to that. So I'll stop here and we will continue into it. Any questions?
I am glad that you
just like write everything down.
Yeah, I mean, like, by the time I'm, like, finishing with something, he's, like, already talking about something new, and I'm, like, I'm not writing down the first sentence. That's Atkinson, where it's, like, every word out of his mouth is, like, very important.
Maybe 6 million on
Conversation?
No, the